welcome to MUNSCI. Today we will be exploring the topic of E, whatever this 2.71828 number actually means, where it comes from, and all of that will be done using materials that have been provided by the IB themselves. Now, if you would go onto the internet right now and search up E formula or derivation of E, you will find the following equation. What does this actually mean? First, let's actually simplify what this means. So this is the same as saying 1 over 0 factorial as n starts at 0, and then we add it once again and we substitute, and with the next positive integer value, which would be 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, and so on. When you put this into your calculator, you will tend to 2.71828 and so on. 2.71828 is equal to E. So this expression here is equal to E. But what we're going to do in this video is actually explore a little deeper using an IB formula that they give us, and use that formula to derive this value here. If you are taking math in the IB, you are bound to come across the following formula, which I'm going to write, whether it be in standard or higher level math, or if it's in AA or AI, you are going to come across the following formula. The formula I'm talking about is a compound interest formula, which is written like so. The future value is equal to the present value multiplied by 1 plus the nominal annual interest rate, R in percent, over 100, and this 100 is to account for the percentage here, multiplied by K, which is the number of compounding periods, to the power, all to the power of K multiplied by N, which is the number of years. Now you can use this equation for any amount of money that you are actually putting into your account, which is being compounded by a certain compounded periods, which is the K here. And for the purpose of this video, we're going to stick to dollars. So let us simplify this equation a little bit. The present value you see here, we can assume that we put in $1 into our account. So the future value is equal to present value, which is 1 multiplied by 1 plus annual interest rate, which we could say is a very generous bank. We could say is 100% interest divided by 100 multiplied by some compounding period. So what this means is, should we have some timeline of a year, we could compound it 3 times or half, like so. After 6 months, where this is 0 months and this is 12 months, we calculate the value and we calculate the value here again. So what we can do is actually set the value to 1 for now, which means that we basically don't have anything in this area here. And we raise it to, once again, we don't have anything in this area again, so we can just say it's N. But N, we could say, is 1 year. Now simplifying this formula gives us the future value should be equal to 1 plus 1 to the power of 1. So what that means is the future value is equal to 2. What this is saying is that when we put in $1 at the start of the year, it becomes $2 after the year. Let's say that we want to, instead of not compounding it at all, we do it every 6 months. This would cause us to input a value here of 2, and same goes at the top here. Instead of writing 1 here, we will write 2. Now that we've input all of this, we will simply solve this. Future value equals 1 plus 100% divided by 200%, because 100 times 2 is 200, would give us 1 over 2 squared. So future value is equal to 1.5 squared, which is equal to 2.25. Now, by simply adding 2 compounding periods, we have added another 25 cents into the money we gain at the end of the year, which is actually quite a lot. So what we can say is, instead of doing it twice, we can do it quarterly, meaning we do it 4 times in a year. Let's change the compounding periods from 2 to 4. Now, when we set it to 4, we get future value is equal to 1 plus 1/4 to the power of 4. Now, if you do this on your calculators, you should get that it is equal to 2.441 and so on. So if we are to do it every single month, we would write 12, multiply this by 12, and do it to the power of 12. And that future value is 2.61. Continuing on. We can see that we've once again added a lot of money, but this time it's not as significant of a difference. In terms of the compounding periods, which is k, and we look at the actual future value that we ended up with, when we compare these two values, we can see that when k was simply 1, we got a future value of 2 at the end. But when k was 2, we got a future value of 2.25 at the end. When k was 4, we got a value of 2.44. Now that we've increased k all the way to 12, we get 2.61. So what we can see is, as the number of compounding periods increases, the future value also increases. And this is obviously good, right? But one thing we can notice is that the amount by which it grows is actually decreasing every time we increase the value of k. If we were to do it every minute, because I would want to gain the most amount of money I could possibly gain, right? Well, I could actually put in a compounding period for k with that number. The number of minutes in a day would be 24 multiplied by 60, which gives us 1,440. Now, this is the number of minutes in a day. In a year, there are 365 days. So we multiply 365 by 1,440, and we get 525,600. Now this we could input in as our value for k. And when we actually put this value in, and we put this in our calculator, so 1 plus 100, or well, we could just do 1 and cancel out the zeros, which we can also do, over 525,600 to the power of 525,600. If you would put this into your calculator, the answer is around 2.718, continuing on. And we can see, as the number gets bigger, as the number of compounding periods gets larger, it tends to e. So if we were to say every second, if we would set the compounding periods to every single second, we would simply say 1 plus 1 over how many number of seconds there are, which I won't calculate, but it would be a lot with tons of zeros. And we said the same thing, tons of zeros, we would be left with $E.